Hey guys, it's Greg. Today I'm going to give you an introduction to the Tensorflow Dataset class. Now this is a very powerful class in TensorFlow, which is used for making pipelines for machine learning and deep learning training. So instead of using NumPy arrays for training, we'll actually see them very briefly for loading, but instead of using NumPy arrays to train on, we're going to turn those NumPy arrays into TensorFlow datasets, and we'll explore what those are and the benefits of them. The main benefit is, well, efficiency, and so it's very efficient to use these things if you do it properly, which I'll show you how to do it properly. And also, as you go into the more advanced stuff, like natural language processing and computer vision, really advanced, up-to-date stuff in that, you'll start to see TensorFlow datasets all over the place because it has to be efficient, or if you're not, you're just kind of wasting your time. So let's get started. It's not going to be too bad. It's just a little bit of a different way of thinking. And before I write our first line of code, I just want to say, think about everything that we do in the mindset of what happens to data later and not right now. Okay, so if you talk about pre-processing, like doing a function over data, think about doing it later and not now. I know that's already a little bit weird, but I will explain to that lots in this video. So I'm going to start with an import numpy as np and an import TensorFlow as tf. And then we're just going to grab the mnist dataset. There's going to be some times when I copy and paste into this because it's just not super related to what we're doing. From tensorflow.curious.datasets import mnist, just going to use the mnist dataset. Hopefully you're familiar. Xtrain, Ytrain, and Xtest and Ytest are numpy arrays. Okay, so this does load them as numpy arrays. And that's proven by, we can ask what their shape is. So xtrain.shape, ytrain.shape, we have 60,000 28 by 28 images. Each of these 28 by 28 images are handwritten digits, and they are labeled by the Ytrain label here. And we have very similar Xtest and Ytest. I'm just going to treat Xtest and Ytest as, we'll actually pass that into the validation data part in model.fit, and we're not really going to have a proper train test validation split. You can think of it really just as train and test. Okay, we are going to make our first example dataset, or our first TensorFlow dataset. I'm calling it example dataset, which is equal to, we'll make one. There's actually multiple ways to make one, which is why they're very useful. But here we are making it a tf.data.Dataset, that's the class, dot from, we're making it from tensor slices. You know, a numpy array, it's basically a tensor. So we're making it from tensor slices. You could also pass like lists and tensors and other stuff. That's kind of as you'd expect. So we'll pass xtrain and ytrain. This is just going to be an example data set. And so right now I'm just going to show you some of its capabilities as a warm up to how we'd actually do it, which I'll do directly after. But just to show this data set in general, I'm just going to load it from xtrain and ytrain. Notice how I did it here. This is not mandatory, but I did it like you have a tuple of the train stuff and the label stuff. That's pretty common, but not necessary. Example dataset is what it outputs as a tensor slice dataset. So really just a TensorFlow dataset. So instead of a numpy array, it has this tensor spec because really it is made up of tensors now. This is why we're making it from tensor slices. These are passing in numpy arrays, but really what it's doing is converting them to tensors. And so they have the first part, this is referring to the xtrain part. It has a tensor spec, or basically a shape of 28 by 28. Whoa, that's already a little bit weird. Why does it not have a 60,000 in there? It's just ignoring that, and I can actually show you, I'll just show you right away, the length of example dataset. If we were to output that, that does show 60,000. And so this whole dataset does still have 60,000 things, but if you were to output it like this, it's just going to show you what it's made of, which is multiple 28 by 28 images, and it's multiple, it actually shows a shape of nothing for this, which means it's a scalar, because this is just a vector of labels, which are numbers 0 through 9, which are labeling what the digit is. Okay, and you can see that they're actually both integers for now. Xtrain does have values between 0 and 255 right now. That's the pixel brightness. And Ytrain has, again, values between 0 and 9 for digits. We do want to do a pre-processing to convert the values from 0 to 255 into just between 0 and 1 as floating point values. That's a standard normalization for computer vision problems. Okay, so we can loop over this thing. For imp and label, That's because we're going to loop over each of these types of things. So we're going to get each time an input is going to be an image, and actually I should really just convert that to image. For image and label, we can loop through the example data set, and we can print the image.numpy, because if we do .numpy, that calls this thing as a tensor, and so if we call it numpy, that shows you what it looks like in numpy instead of a tensor. Label.numpy as well. If we print that, and I'm just going to do a break so that it only does the first one. So this is the first image and label pair. This has the image, which is 28 by 28, and it has a bunch of pixel values between 0 and 255. And over here, that's the label, showing that it represents a 5. Something a little bit easier to see is if I just do shape for this part, then you should see it's a 28 by 28 image, which is a 5. So if we loop over the data set like this, you'll see we actually get tensors. They're stuck as tensors, and you can access their numpy if you want to like that. Okay, I'm going to write that function that's going to normalize a single image, because what we're actually going to do is map to the whole data set. The data set is a bunch of image label pairs. What we can do is we're going to write this one function that takes in an image and label pair, and it returns something done to that image label pair. So it still returns an image and a label, or at least it still returns a tensor and another tensor, but we're going to have done something to them, which in this case is going to be just dividing them all by 255 and converting to a float. So if we do define, so I should go up a bit, define normalize image, which takes an image and a label. We're just taking the label because it's we're just going to return it back. We're not really doing anything interesting with it. It's just easy this way. If we return tf.cast, so this is converting image to a tf.float32. And then if we divide that by 255.0, that is dividing that whole tensor, and then we can return label. So here we're still returning, we take in an image and a label, which are two tensors, and then we're going to return an operation on that tensor, which is just dividing by 255, and then we're going to return the label as is, because we don't really want to touch that. Now we're writing it in this way so that we can do example dataset is equal to the example dataset dot map. We're going to map, which maps a function to each of its parts. Each of its parts is an image and label. It has 60,000 images and labels, and so it's mapping to each of these 60,000 images and labels. We're going to choose the normalize image function, and then there's also this other thing we just pass in, which is we don't have to worry about it at all. For efficiency, you have to do num parallel calls is equal to tf.data.autotune. It's auto-tuned, like it's already tuned, and so that's just something that it figures out. Now if we write example dataset, then we can see it's a parallel map dataset. It's really just a dataset, and it has the same shape and stuff before. The only real change is you're going to see a float 32. If we were to loop through, and so I'll just grab that same looping through idea that we had before, and if I take away if I just do it for now, you should see it looks exactly the same. But if we take away the shape, then you should see that the values are between 0 and 1 now, and they are floats. Okay, I'm just going to delete that. Actually, I'll leave it as just the shape for fun. Okay, so we did a mapping there. And this is the first time that I'm going to explain, first of many, that I'm going to explain what I said at the beginning there, which is I said, try and think about things happening later. Think about, say, a pre-processing function happening later instead of now. And what's a little bit weird about that is because clearly it is happening right now. And so if we did this map thing over here and we loop through it, we can see that it's done. Okay, it clearly has already mapped that function because it did change everything already. However, it's actually not doing it here. It's doing it here, which is really weird because here, this is where you're saying the map. And so in normal Python, when you do a map, then okay, it'll do the map. And same thing with other NumPy-like stuff. But here, it's actually doing it over here. And so what the map is doing here, it's saying, hey, later, do this. So when you iterate through, when you go through the data set, I want you to do this to the inputs. And so here, We made a function that tells you what to do, and then we literally are telling it, hey, dataset, when you load up the dataset, do this. When you iterate through the dataset, do this. But we haven't done it yet here. Here, we have done it. And so when we go through image and label, what it's doing is with this num parallel calls kind of manner, it's mapping this function to those images and labels. And so it's efficient that way, and it also is convenient for some things. What you'll notice is I could run this 50 times, but it's still going to return the exact same values every time. If we had something randomized in there, it might not. But this is a deterministic function. It simply divides the values by 255. So no matter how many times we do this, even though it's happening here, it's still only happening the once, because what it's doing is when we iterate through this data set, it says, hey, look at the data. Look at that MNIST data from the beginning. Okay, we got the data. What do we want to do to it? Well, I've told you what we want to do with it. When you load it up and when you actually iterate through it, we want you to map this normalized image function to the inputs. Okay, so it grabs that MNIST data, and then it does this mapping function, and then it prints the result. So the reason that it's not changing every time is because it's still reading from that initial MNIST file, and then it's doing this every time that it loads into memory, basically. Okay, so that's why we call them pipelines. That's why I made sure to have that in the name of the video, because this is about defining pipelines in TensorFlow. And so we'd want it to be built like this, so that whenever we do something like this, where we say like a dot map, and we'll see other stuff where we do dot other things like shuffle and batch, it's saying, what are we going to do when we're in the training function? When we do model.fit, each time you load up the data set in a new epoch, what do you want to do to that data? Well, we're going to be defining this pipeline where one of the first things we'll do is map, and then we'll do some other things as well every time in the epoch, okay? And so another thing is we'll see this thing called cache very soon, which cache is going to make things more efficient, because you might just want to do this literally once and then save the result. You could do that. And so instead of just looping through every time and it doing it every time it loads up, we could actually just go in here and say example dataset is equal to example dataset dot cache. And then if we output example dataset, well, it's not going to look that different, but it's cached. And so if we were to loop through it now, guess what? It still looks exactly the same. Since we did this map thing, we already told it to map. It's saying, hey, you want to do a map when you load up the dataset. But if you don't want to do that every single time, if you want to save the results here, well then, hey, we can write cache. And so now what it's done is said, hey, okay, we've saved the process of the mapping. Don't do that mapping every time we load up it in memory, but it's still going to look the same to us, because whether it happens in a streamlined fashion, whether it maps it and then it loads it in, or it's just loading it in from the already mapped stuff, it has to look the same to us. The change of what happens in the computer is just an efficiency standpoint, and so it's going to do things a lot faster when you do cache in the right spot. Okay, so that's cache, and that's the pipeline function. If this all does not make sense and you're just listening to me and waiting for me to do more things and hopefully it'll make sense, that's fine. I will do more, show the pipeline, and explain it probably again. Okay, so after we cache it here, we are going to now shuffle it, because it's pretty common that when you do an epoch, when you go through the training process, every epoch, you're going to shuffle the training set. And so again, this is still just on this example data set for now, but we'll do example dataset is equal to example dataset dot shuffle in the length of the example dataset. And then we're just going to loop through it exactly like we did before. I'm just grabbing that from my other copy. For input and label, I prefer image. For image and label in the example dataset, put the image numpy shape and the labels numpy. So here, okay, this is a 7 now. Before it was a 5. And if I run this again, well, it's changing because it's shuffling. Is it? No, it's not. When we do it here, it's not literally shuffling the data set as it is. It's defining the pipeline. What the pipeline is so far, what have we done? We did the map, we did the cache, and we did the shuffle. Since we did the map and the cache, really that's equivalent to just reading and starting the pipeline from the already mapped stuff. And so it's reading from that. And so when we go through here, it reads from that cached stuff. It doesn't do the map. It doesn't have to do the map anymore because we cached it. And then it does the rest of the pipeline, which is just shuffle it. So really all it's doing is just shuffling that already mapped stuff. And so this is our pipeline so far. Okay, we're going to eventually again pass this into model fit, and then it'll do that pipeline every epoch. Okay, I'm going to stop saying that every single time now, but just know that we are creating a pipeline when we do this dot something, dataset dot something. So if we do example dataset is equal to example dataset dot batch, say 32, actually I'll do 64 because 32 was a little slow when I did it. And so we just batch the results. Example dataset is a batch dataset. Really, it's just a TensorFlow dataset. But here we see a none 28 by 28 and a none here. So basically, this is showing you in a weird way that it is batched. And again, if I like just looping through it here, I'm looping through it. And what do we see? We see that the shape of each of them is 64 because we batched them into 64s and 28 by 28. And then you should see, since we had a batch of 64 images, then we have 64 responses as well. So again, I'm looping through the example dataset and I am stopping it after the first result, but the first result now is a batch of stuff instead. And so this image is a batch of images, and this is a batch of labels instead. So now what the pipeline is so far is, since we cached the mapping stuff, well, it's going to just read from that mapped stuff, and then it's going to shuffle it randomly, and then it's going to batch them. So now we're shuffling, we're randomizing it, and then we're batching that randomized stuff, so we get randomized unique batches. And then well, we have batches. What do we want to do with them now? There's only one more thing, which other than feed it into a model, there's one more thing, which is this prefetch thing. Example dataset is equal to example dataset dot prefetch tf dot, why can't I spell that? tf.data.autotune, and then example dataset. Now there's really little explanation I'm choosing to give on this. It's going to look exactly the same here, aside from it writing prefetch there. But basically what this does is telling TensorFlow, and again, it's part of a pipeline, is saying at the end here, since it's the last thing, this is the last thing we're going to do. At the end here, it's telling it to kind of grab other stuff before it moves, before it's done dealing with the current stuff. And that's a little bit confusing, especially in the context of what we've already been saying. But don't really worry about this. I'm just going to leave this for now, as this is an efficiency thing. After you've done everything in the pipeline that you want to do, just do this prefetch thing, and so that will speed things up. Okay, now that we've seen that, it's going to be tremendously easy to do the rest of this stuff. We're going to load up the training data set and prepare that as above, and the test data set and prepare it similarly to as above, although I'll explain some differences where it makes sense to have some differences. And then we pass that to model.fit, and that's really it. Okay, so I am just going to copy this in one at a time, because it's pretty much exactly what you saw earlier, except with the different name of a variable. Train dataset is a tf.data.Dataset from tensor slices with xtrain and ytrain, because that's for training. We are going to do a mapping to that. And so we do train dataset is train dataset.map, the normalized image. Non-parallel calls is tf.data.autotune. And so that is saying the first step of the pipeline is to do that map. And now the second step of that pipeline is going to do train dataset is train dataset.cache. So you want to do that map and then cache it. So now that's really not saying anymore, this is part of the pipeline. We've done that. When we do it, we do the map and read from the cache. And so this literally actually does cache it. It does that map, does the cache. So now we'll be reading from that cache instead of really doing that as part of the pipeline later. Now what we want to do after we've read from that cache, we'll do train dataset is train dataset.shuffle. So every epoch you want to shuffle it, and we pass the length of train dataset because that's just the number. You generally pass the number as shuffling, and I don't think I said that before, but you pass the length of the dataset as the shuffle parameter. we want to do a batch. And so train dataset is train dataset.batch. We'll say 32, or you could do 64, or many other multiples of 2. And then for efficiency standpoint, we want the last thing in the pipeline to be train dataset is train dataset.prefetch with the auto-tune parameter there. Okay, so train dataset at the end of all of this, well, it's calling it a prefetch dataset. Well, what has it actually done? It mapped it and cached it so that we have saved that stuff. And then it said for the rest of the pipeline, what we're going to do is shuffle that cached stuff, batch that cached stuff, and prefetch it. Do that every epoch. Now, test dataset is going to be a little bit different, but very similar. We're going to get test dataset is equal to tf.data.Dataset from tensor slices with xtest and ytest. So we pass in that numpy arrays as xtest and ytest. You could have a validation dataset as well if you split up the numpy arrays such that you added a validation set, but we're not going to do that. We're going to do test dataset is test dataset.map normalize image with that num parallel calls. That's reasonable because you still want to do that mapping to the test information. You still want to cache that. However, you do not want to shuffle it at all. We wouldn't want, well, I mean, you probably could shuffle it, but there's no point of shuffling it. We also can do the batching first before the cache. So here for training, we do cache right after, but here we can actually do test dataset is test dataset.batch. Again, we'll say 64 because of the fact that you're not shuffling and you're okay with the fact of getting the same batches every single time, then we can do map and then batch and then cache so that we've basically cached those batches. If that doesn't make sense, don't really worry about that too much. Test dataset is test dataset.cache. And so we've cached all of that information above. So every time we're doing an epoch involving the test dataset, what do we actually do? We're just going to do this thing similar to above. Test dataset is test dataset.prefetch tf.data.autotune. It just tells you to that thing to prefetch. And then if we output test dataset, nothing too interesting, prefetch dataset, and we've done this stuff to it. We've mapped it and batched it and cached that result. And we're just saying just do the prefetch. Okay, here we are defining the model. I am definitely copying and pasting this because hopefully you have seen some sort of TensorFlow model before. If not, and this is your first one, well, okay, this is going to be a little bit confusing, but we're going to make a model, and I will explain it. From TensorFlow.curious.models, import sequential. From TensorFlow.curious import layers. So we're going to build a sequential model out of layers. The model I'm going to be using is a convolutional neural network, one that I just kind of made up for myself for fun. There's no average pooling aside from the global average pooling, and there's no batch normalization as well, which there probably should be. But I take an input layer, which takes a 28 by 28 image. Since we're going to do convolutions, I'm going to add just a reshape an extra 1 onto the end there. We're going to do an 8 filtered convolutional 2D with a 3 by 3 window, and the strides is 1 by 1. And for fun, I just said do that 5 times. After that, we're going to do a global average pooling. You could do why am I forgetting the term? Flatten, but average pooling is usually better. And then we're just going to do some normal neural network stuff. Dense 32, 32, 32 for fun. And 10, we do a 10 activation softmax because the goal of this network is to try and predict the probability of each of the classes. So the probability of 0, 1, 2, 3, up until 9. So there's 10 different digits. We want the probability of each of those. And if we do a model.summary, you should see that model there. 28, it starts at 28 by 28, converts to 28 by 20 by 1, does some downsampling with the convolutions. It does some global average pooling. It does some dense stuff. Eventually gets it to that 10 activation softmax layer. Okay, again, some other very conventional model stuff for this scenario. I'm just going to paste in from, I just have to do this a little bit, from TensorFlow.curious.optimizers import atom, from TensorFlow.curious.losses import sparse categorical cross entropy. It's categorical cross entropy because of that softmax, and it's sparse because the way that the labels are prepared, as is in MNIST right now, is that each of the labels are numbers. As we saw, they were scalars, and so they're just numbers representing the digit and not the one hot encoding. Model.compile with the loss as that loss, with the optimizer as that optimizer. I set a learning rate equal to that. We could make that smaller or faster, or smaller or bigger, depending on what we see. And metrics equals accuracy is going to be fine. Okay, so we compile that model. I'm not sure if I've done this in tutorials before, but if this is your first time seeing it, it's very useful. From tensorflow.curious.callbacks import early stopping. So a callback where at the end of every epoch, it's going to call this function, early stopping, with a patience of 5, which basically says if the, by default, this is going to be looking at the validation loss. If the validation loss does not improve after 5 epochs, like it does 5 epochs in a row with the validation loss not improving, the model basically says, or I'm telling it to give up at that point and just stop. So that we can do a model.fit like this. Model.fit with train dataset, instead of x train and y train like NumPy arrays, you just pass the train dataset. Epochs is 100. It's not going to do nearly 100 epochs. I think it did 32 when I was practicing this earlier because of the early stopping. Validation data, we're just going to treat as the test dataset, and then callbacks is going to do that early stopping. Now make sure you are doing a runtime on GPU for this, otherwise it will be very, very slow. I'm just going to let that run, and I'll talk to you after it's done, and I'll show you the result. Okay, it's all done after, what is this, 46 epochs. That took more than the 32 it did when I ran it earlier. Validation accuracy, it finished off with, actually it should have been, it probably saved this model, which was the validation loss hit a low at this 0.0838. It said, no, it did worse than that, 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 five times in a row. And so it said, no, actually, we're going to use this model right here. Okay, so that's pretty awesome. That's really it. I just want to explain one more time that every epoch here, so you can see each run through the dataset, what is it actually doing? Well, when it's doing the training data stuff, it is going to do the pipeline that we laid out. We did a map to the input, but then we cached that. So it's not doing that every time because it's already cached that and it's reading from that cache. So it reads from that cache and then it shuffles it and it batches it and then it prefetches, which is just some efficiency thing, each epoch. So it shuffles it and batches that cached data every time, every epoch. And then the test stuff, whenever it does the test stuff, well, we mapped and then we batched and we cached. So it's not doing all of this stuff every epoch. We're just reading from this mapped and batched stuff because we already did that. And then it's still going to do a prefetch because it's an efficient thing to do. Okay, I hope that made a lot of sense. I know that I explained the pipeline thing 50 times. If you still don't understand the pipeline thing, I get it. It's a confusing thing. I tried my best to explain it as best as I could and as many times as possible, because that's the key here. If you understand that pipeline thing, if you're like, Greg, shut up, I understand the pipeline thing, mission accomplished. I'm so happy to hear that. If you still feel like you don't understand like what cache is doing, and you don't have to know what prefetch is doing, although you can look it up if you want. If you still don't understand what I'm talking about when I make this pipeline and about things happening later, about things happening when we read in the data or when we do an epoch, that's really important. And so I'd recommend maybe watching this again, maybe a little bit slower, and making sure that you understand, you listen to the individual words that I've been saying and exactly what that means, because it's really important. I hope that helps, and drop a like on the video if you found this helpful, and I'll see you later, guys. Thank you.